Dear students, today we discuss about some creative question from aliphatic hydrocarbon. Here, given this term CH3, CH2, CHBr, CH3, that means this is 2-bromobutane. And when it reacts with sodium hydroxide aqueous solution, then we get the compound A. And when the compound reacts with alcoholic sodium hydroxide, then we get compound B and C. The percentage of B is 80% and percentage of C is 20%. And now our question is, first question, explain the mechanism of the preparation of A. Here we see the compound. If we see the compound CH3, CH2, CH and CH3Br. This is 2-degree alkyl halide. This is 2-degree alkyl halide. And if we see the compound, we know that 2-degree alkyl halide gives SN1 reaction mechanism. SN1 reaction mechanism. Here, one for unimolecular. This one is N represent nucleophilic and S represent substitution. So it shows unimolecular nucleophilic substitution reaction. That means SN1 reaction mechanism. Now we see the reaction mechanism. SN1 reaction mechanism. At first, we produce nucleophile from sodium hydroxide alcoholic. It produces sodium ion plus hydroxyl ion, OH minus. And in this reaction, this is nucleophile. In our first stage, the compound is CH3, CH2, CH, CH3, Br. In the first step, the alkyl halide first ionized to form a carbocation CH3, CH2, CH, CH3 and halide ion, that means bromide ion. And step 1, this is step 1. This is step 1. And second step, step 2, CH3, CH2, CH plus CH3 plus OH minus. And second step, this hydroxyl ion, that means this nucleophile attack the carbocation and we get the product CH3, CH2, CH, CH3, OH. That means in the second state, the nucleophile attract the carbocation and we get the product. In the reaction mechanism, this is slow step. First one is slow step, and the second one is first step. And here in slow state, only reactant is used to reaction, and that's why this is unimolecular reaction, and this is the mechanism of preparation of A. In question number D, here we get between B and C, which one show stereoisomerism? If we see the reaction CH3, CH2, CH, CH3Br, if it reacts with sodium hydroxide alcoholic, then we get two products. First one is CH3, CH double bond, CH, CH3, and the second one is CH3, CH2, CH double bond, CH2. Now if we see the reaction, here 2 hydrogen present and here 3 hydrogen present. This is elimination reaction. If this hydrogen, this is alpha carbon, this is beta, this is also beta, and this is gamma. If hydrogen eliminate from this beta carbon, then we get the product butene 2. And if this hydrogen eliminate from this carbon, then we get butene 1. That means here we get two products. There is a rule that is known as size F rule. Size F rule is there are haloalkanes that can undergo elimination in two different ways, resulting into different products. Here we get two different products: alkenes with less number of hydrogens. Alkenes with less number of hydrogen on the double bonded carbon atoms are preferred products. So according to size F rule, we can say that this is the preferred product for this reaction, and that's why we get 80% product butene 2 and 20% product butene 1. Now we discuss about the isomerism of these two products. Students, here the question is between B and C, which show stereoisomer between B and C. According to size F rule, we discussed that this is B and this compound is C compound. So now we see the stereoisomerism of this compound. Here restricted double bond rotation is present because here double bond is present, and that's why the bond is restricted. And if two groups attached to the double bonded carbon atoms must not be same. If this condition shows any compound, that compound show geometrical isomerism, that is geometrical isomerism. Now we discuss about butene 2. What is butene 2? Here butene 2 CH3, C double bond C, CH3 H, H. Here we see that here double bond present, so the bond is rigid. That means bond rotation not occurs here, and the attached group in this carbon is different, and this one is also different, and that's why B compound shows geometrical isomerism. But if we see the compound C, that is CH3 CH2 C double bond C H H H, here this bond is restricted double bond because here no rotation occurs due to double bond. But this group, this two group, that means here two hydrogen is present, that's why this compound cannot show geometrical isomerism, and that's why B compound, only B compound show geometrical isomerism, that means stereo isomerism. And this product we get for B butene 2, we get two isomer, that is CH3 C double bond C CH3 H H, and if the bulky group in a restricted double bond present in same side, that the compound is cis isomer. Cis isomer, and this is trans isomer because the bulky group is opposite side present. Trans isomer. So we can say that this is cis butene 2 and this is trans butene 2. Dear students, now we discuss about question number 2, CQ2. Here given the reaction ethanol, this is ethanol, reacts with potassium dichromate and concentrated sulfuric acid. Here partial oxidation occurs, and we get a compound P plus water. And reaction 2, in reaction 2 we see that here given propanol 2 that reacts with potassium dichromate and concentrated sulfuric acid, partial distillation, and we get compound Q plus water. Here the first question is, how can you convert P to methane, right, with equation? And our second question is, which one between P and Q is more reactive to nucleophilic addition reaction? So now at first we discuss about the two reaction. If we see the reaction, first reaction, reaction 1, here CH3 CH2 OH, this is ethanol. Here partial oxidation occurs, that means potassium dichromate plus sulfuric acid concentrated, then we get nascent oxygen and potassium dichromate K2Cr2O7 H2SO4 concentrated sulfuric acid, and in this reaction we get ethanol CH3 CHO. In this reaction if we see CH3 CH and OH reacts with nascent oxygen, and here this hydrogen and this hydrogen reacts with nascent oxygen, and we get the compound CH3CHO. CH3CHO. This is ethanol. So the compound P is CH3 C double CHO. that means ethanol. And in our second reaction, here given propanol 2 CH3 C H OH CH3 and potassium dichromate K2Cr2O7 H2SO4 concentrated sulfuric acid, and then we get nascent oxygen from here because partial oxidation occurs, and in this reaction we get CH3COCH3, that means propanone 2. This is propanone 2. In this reaction, if we see CH3CH CH3 OH plus nascent oxygen, here this hydrogen and this hydrogen reacts, and we get CH3COCH3 CH3COCH3. That means we get propanone 2. So here Q compound is CH3COCH3. that means propanone 2. Propanone 2. If we use another color, because the red color is fade now, P is CH3CHO, that means ethanol, and Q is CH3COCH3 propanone 2. Now we see the question number C. How can you convert P to CH4? Write with equation. Here answer question number C. How can you convert P to CH4? We see that in our first reaction, CH3 CH2OH reacts with potassium dichromate K2Cr2O7 H2SO4 concentrated, here nascent oxygen, and we get ethanol CH3CHO. This is ethanol. If ethanol is oxidized with concentrated sulfuric acid, then we get ethanoic acid. That means if CH3CHO again reacts with potassium dichromate K2Cr2O7 H2SO4 concentrated sulfuric acid, then we get ethanoic acid CH3COOH. After this reaction, this ethanoic acid CH3COOH reacts with sodium hydroxide, and it produces sodium ethanoate. That means CH3COONA plus H2O. And here if we use soda lime, soda lime is the mixture of calcium oxide and sodium hydroxide. That means CH3COONA reacts with soda lime NaOH CaO. This is soda lime. Then this hydrogen reacts with this carbon, and here we get CH4 plus Na2CO3. That means if sodium ethanoate reacts with soda lime, then we get methane and sodium carbonate. So by this reaction we get methane from ethanol. Dear students, now question number D. Which one between P and Q is more reactive to nucleophilic addition reaction? Here we see, according to the stamp, P compound is CH3CHO, that is ethanol, and Q compound is CH3CO, CH3 propanone. In nucleophilic addition reaction, we see that in the reactivity of aldehyde and ketone, there are two effects. The first one is electronic effect, and the second one is steric effect. First one is electronic effect, and second one is steric effect. Here, first one is electronic effect. We know that alkyl groups are electron donating group because of positive inductive effect. So alkyl group, that means methyl group, decreases the positive charge of carbonyl carbon, and that's why the chance of nucleophilic attract decreases. If we see in ethanol and propanone, in ethanol one methyl group is present, and it push electron towards this carbonyl carbon, and that's why the positive charge of carbonyl carbon decreases. And if we see propanone, here two methyl group is present, and two methyl group push electron towards this carbonyl carbon by positive inductive effect, and that's why the positive charge of this carbonyl carbon decreases more and more. And according to this electronic effect, we can say that ethanol is more reactive than propanone in nucleophilic addition reaction. Now, what is steric effect? When more alkyl groups become attached to carbonyl carbon, it limits the attack of nucleophilic attack. The process by which bulky alkyl group prevents nucleophilic attack is known as steric effect. Here we see in ethanol there is one alkyl group. There is one alkyl group present, and in propanone there is two bulky group is present, or alkyl group is present. So steric effect is more. Steric effect is more in propanone. Steric effect is more in propanone. As a result, nucleophile cannot easily attack the carbonyl carbon of ketone. So we can say that according to our discussion, ethanol is more reactive in nucleophilic addition reaction than propanone. Thank you.